This video is one of a series of videos I've made for students who are learning physics to prepare to enter a diagnostic medical sonography program. To find other related videos, please see my playlist, Physics for Diagnostic Medical Sonography Students. In our previous video, we covered these basic definitions. We covered the concepts of position, displacement, average velocity, and average acceleration. Just to review quickly, the first thing I have to be able to do is locate an object, and we do that by setting up a one-dimensional coordinate system. So for example, I specify where the origin is, and then I can simply mark my coordinate system. And if I wanted to specify the position of an object, for example, if there were a person standing right here, I would say their initial position, x0, would be -2 meters. We then talked about displacement. Displacement is simply the change in position, so we use delta. And in this case, delta x is the displacement, and that's simply the final position minus the initial. So for example, let's say that my person ended up over here at the 3-meter mark. Their final position would be 3 meters, and their displacement, delta x, would be x minus x0, so 3 minus, but notice that x0 is negative, so minus -2, which would be equal to 5 meters. So that would be the displacement for that person who started at a position of -2 and ended up at a position of +3. We then talked about average velocity. We defined it as the displacement over time. And we also defined the average acceleration as the change in velocity over time. Remember that velocity will have units of meters per second, since displacement is going to be measured in meters and time in seconds. Acceleration will have units of meters per second for velocity over seconds. And remember that we can write that in a shorthand way as meters per second squared. We want to continue with our study of one-dimensional kinematics, and we're going to be looking at a special case. We're going to be looking at the special case of motion with constant acceleration. Now, there are a number of situations where the acceleration is constant, or at least approximately constant. I mentioned here a car accelerating or braking. So for example, if you're driving your car and you're holding the gas pedal down, in a pretty even way, the acceleration of the car is probably pretty much constant. Same thing if you're stepping on the brake pedal in an even way, then the car will also be accelerating at a constant negative rate. Another example is the acceleration due to gravity near the surface of the Earth, and we'll talk about that a little bit later in this video. Well, it turns out that when the acceleration is constant, then we can get the following two kinematic equations. And these we'll refer to as our kinematic equations. You'll notice that these are all instantaneous quantities. So what do I mean by that? I mean, notice there's no v bar or a bar here. We're not talking about average quantities. Remember that if there's a naught on a variable, it means the initial value. And if there's nothing on the variable, it means the final value. So here, x0 would be the initial position, v0 the initial velocity. And what that first equation allows us to do is find out where the object will be at a time t if we know the initial position of the object, the initial velocity, and what the acceleration is. Notice there's no bar over the acceleration because it's constant. It's never changing. The second equation would allow us to find the final velocity based on the initial velocity and again the acceleration. So if I wanted to know how fast an object is going after a certain number of seconds, as long as I know the initial conditions, then I can find the final velocity. One of the things that you're going to want to do is start making a table, because one of the things that's always challenging about learning physics is there's so many symbols and they're different units, and we've got to understand how the quantity and the symbol and the units all relate. So up to this point in the course, we've had initial position. Remember, that's x naught because naught means initial. And generally, we're going to measure position in meters. Our final position, we denote just with an x. Again, the unit would be meters. Average velocity, that symbol is a v with a bar over it. That would have units of meters per second. Initial velocity would be v naught, and that has units of meters per second. Final velocity is v, again units of meters per second. Time is t, units of seconds, and acceleration is a, and remember those units are meters per second squared. So when you're given a word problem, you have to be able to translate the words to the correct symbol, and that's why it's important to make a table like this and keep track of it. Let's look at an example. A car slows down from 25 meters per second to 15 meters per second in 9 seconds. And we're asked to find the acceleration and the car's final position. So one of the things we always want to do is we always want to draw a picture and identify what we know and what we don't know. So that's really the key. So I'm going to draw my car here. And I'm going to say the initial position of the car is x naught equals 0. Because I can always say wherever I want the origin to be, I'm just going to always pick it to be where the object starts. I'm also told that the initial velocity is 25 meters per second. So notice v naught is equal to 25 meters per second. Now you'll notice the car is slowing down. It doesn't come to a stop, it's still moving, but obviously it will have covered some distance. And so our final position in the problem is one of the things we're trying to find. We don't know it. However, we do know that the car is moving at 15 meters per second and that it took it 9 seconds to get that far. You'll notice that what we've done is we've carefully read the problem and we've identified all the things we know. Now, there are two things we don't know. We don't know x, and notice that's one of the things we're trying to find. And we also don't know the acceleration. I'll put that kind of in the middle here because the acceleration is the same throughout the entire problem, where these are just initial values and final values. Okay, so if we want to find the acceleration, the equation that we're going to want to use is the one that is the simpler of the two. You'll notice that v is equal to v naught plus at is going to allow us to solve for a because we know v, we know v naught, and we know t. The only thing we don't know is a. So let's go ahead and solve this algebraically for a. The first thing I'm going to do is I'm just going to swap the sides of the equation. So v naught plus at is equal to v. And now I'm going to subtract v naught from both sides. So I get at is equal to v minus v naught. And now finally, I'm going to divide both sides by t. So a is equal to v minus v naught divided by t. And you'll notice we're now ready to plug in our values. So a is equal to the final velocity, that's 15, minus the initial velocity, that's 25, divided by the time, which is 9. So if you do this on your calculator, what you should get is negative 1.1 meter per second squared. Now remember what that negative sign means. It's telling you that the car is losing 1.1 meters per second for every second that goes by. So it's losing velocity every second. And that makes sense because clearly the car is slowing down. So I'll just make a note here that minus sign is because the car is slowing down. In everyday language, we might use the word decelerate for that, but in physics, we use the term acceleration to be either speeding up or slowing down. And we want to just fill in here that we've now found the acceleration, which is negative 1.1 meters per second squared. So to find the position, we're going to want to use that second equation, that x is equal to x naught plus v naught t plus 1/2 at squared. Now the good news is we're already solved for what we're looking for, which is x. All we have to do is plug in the values. The initial position was 0. The initial velocity was 25. We've got to multiply that by the final time, which is 9 seconds. And then we have 1/2 times negative 1.1 for our acceleration. And then we've got 9, and we need to square that. So when you calculate this out using your calculator, that first number should come out to be 225. And then that second term, when you figure that out, you'll notice it's going to be negative. And I got negative 44.55. And so when I do that math, I get 180.45. And in this case, since we only had a couple digits in all of our values, we're going to just round that to a final position of 180 meters. So here's an example for you to try on your own. What I'd like you to do is pause the video and see if you can get through this all on your own. Draw the picture, do the work, and then restart the video and see if you get it right. Okay, well let's go over it together. So we've got a car traveling to the right. We've been given the initial velocity. So you'll notice the first thing we have to be able to do is understand that that's v naught. We're told that the car comes to a stop. And so notice that's telling us that the final velocity is 0. You'll also notice that we've got the time. And so we're asked to find the acceleration and, again, the car's final position. We always want to draw a diagram so that we can keep track of what's going on. So again, my car here is at an initial position of 0. I'm arbitrarily always going to say the starting position is at the origin. We've got the initial velocity, which is 32 meters per second. And then the car comes to a stop over here. And we don't know where it is when it comes to a stop. That's something we're trying to find. But we know that it took 5 seconds for the car to stop. And since it stopped, we know the final velocity is 0. So those are the things that we know. Okay, so we want to find the acceleration, and we want to find the final position. Very similar to the last problem that we did. So I want to find the acceleration by using v is equal to v naught plus at. Again, you'll notice that we know v, we know v naught, we know t, so we only have one unknown, and therefore we can use that equation to solve it. And so I'm just going to skip the steps that I showed you previously and just go to where we get what a is equal to. So again, you should be able to do these algebra steps like we did on the previous slide, or previous couple slides. But we get to a is equal to v minus v naught over t. And when I plug in the values, notice v is 0, and then I'm subtracting v naught, which is 32, and then I'm dividing by 5 seconds. And what we get when we do that is we get negative 6.4 meters per second squared. You'll notice that it makes sense that the acceleration is negative because the car is slowing down. So in other words, the velocity was decreasing each second. Then we can finish the problem by using the other equation, x is equal to x naught plus v naught t plus 1/2 at squared. So now we just need to plug in our values. X is equal to 0 plus v naught, which is 32, times the time, which is 5, plus 1/2 times negative 6.4 times 5 squared. And when you do that math, you should get a final answer. X is 80 meters. Let's look at the acceleration due to gravity. Let's start with this question. Which will hit the ground first, a big mass or a small mass? So let's say I have a little rock and I've got a big rock. Which do you think will hit the ground first if I drop them at the same time? Well, the answer is they will land at the same time. And that's because the acceleration due to gravity is constant. In other words, both objects' velocities are going to change in the same way. Now, there is one little point we have to make here. We say in the absence of air resistance, because we all know if I took one of my objects and I made it be a feather, that feather is just going to kind of float down. That's because of air resistance. But if we take dense objects like a rock or a pebble, those are going to fall at the same rate. So we call that rate the acceleration due to gravity. The magnitude of the acceleration due to gravity is denoted by the letter g. And the value here on Earth is 9.8 meters per second squared. Now, we're not going to do vertical motion problems in this course, but I want to just remind you again what we mean by an acceleration. Remember that an acceleration is telling us how the velocity is changing every second. So when we say that the acceleration due to gravity is 9.8 meters per second squared, remember we can think of that as 9.8 meters per second per second. So just to think about what does that mean? If I took an object and at t equals 0, I dropped it, so the initial velocity is 0. If the acceleration due to gravity is 9.8 meters per second, that means after 1 second, that object would be moving down with a velocity of 9.8 meters per second. So it's gaining 9.8 meters per second for every second. So if we looked another second later, we would see that the velocity would have gained another 9.8 meters per second. Or in other words, we would now be up to a total of 19.6 meters per second. So that's what it means. We're going to find that we're going to be using g to help us calculate the weight of an object. And we'll see that when we get to Newton's laws, which are our next topic.